So one of our essential skills is balancing nuclear decay reactions. And of course, any radioactive nucleus, we call it a radioisotope. And the key is to get the top numbers and the bottom numbers, in other words, the atomic masses and the atomic numbers, to balance. In other words, we need the left-hand side to be equal to the right-hand side. And so one of our key skills here, besides getting them to balance, is realizing how to do radioisotopes or isotopes in general just from the words. So our first example is the product of alpha decay of uranium-235. So how would we write that out? Well, first off, I know that uranium is the symbol U. And the 235 means it's the top number. Now I look on my periodic table and I find that the atomic number is 92. So uranium-235 has that symbol right there. Now, since it's a decay, we go ahead and put an arrow across and we indicate, well, it's alpha. What is alpha? Well, it's a 4,2 helium. And so we write down 4,2 helium. Now we want to know the product, which means it's something over here. Well, we see that we have 235 on the left-hand side and we have 4 plus something on the right-hand side. Well, what is that something? Well, it's got to add up with 4 to make 235, and that would be 231 for the top. And then we look at the bottom and we say, well, we have 2 on the right and 92 on the left, so what plus 2 is going to give me 92? And we say, well, that's 90. And so we have some sort of unknown element which has 231 on the top, 90 on the bottom, 231 for its mass number and 90 on the bottom for its atomic number. And we look on our periodic table and we find that it is thorium. So the product of alpha decay of uranium-235 is thorium-231. And we can actually write that off to the side here for thorium-231. In our next example, we have what is the product of beta decay of carbon-14. And so first off, what is carbon-14? We write it over here. Well, carbon has a symbol C, and 14 is the mass number because that's what carbon-14 means. And then, of course, it is element number 6. And we're going to draw an arrow, and hopefully we can remember what is a beta decay. What's a beta? A beta is an electron, and it has a -1 charge and a mass of essentially 0. And remember, this electron from beta decay is not coming from the electrons that are surrounding the atom. They're actually coming from the nucleus. When a neutron decays to a proton, it releases an electron. And so we put down here -1 and 0 for our beta. And we need to know what is the product here. Now you have to be careful with beta decays because what do we have here? We have a -1 on the bottom. But let's do the top first. So what plus 0 gives me 14? Well, that's easy. That's 14. But what plus -1? What plus -1 gives me 6? And that's actually 7. And it's a common mistake to say, oh, it must be 5 because 5 plus 1 gives me 6. No, you're subtracting off that -1. And we look on our periodic table to find what is element number 7, and it is nitrogen. So we just made nitrogen 14 from the decay of carbon 14. So now, let's come on down here. Now here's an interesting one. We need to decide what are we starting with. And so what's the starting nucleotide or nuclide? Nuclide. We have an underline. And we're going to positron decay. Now, a positron is a positively charged electron. And we're also told that the other product is xenon-131. This time we're given the atomic symbol. And now we have to work back towards the reactant side. Well, let's see, 0 plus 131, well, we have to make sure the tops or the atomic mass numbers add up, and that would be 131. And we look over here to the right-hand side on the product side, and we see plus 1 and 54 for the atomic numbers. Well, of course, electrons don't have atomic numbers, but we treat them the same way and say 1 plus 54 gives me 55. And so we check and see the top numbers add up, the bottom numbers add up, and it's balanced. And we look for element number 55, and it is cesium. There it is. We have found the missing piece out of this equation, even if it's on the reactant side. Now, we also have to balance, well, we just saw that one. Let me go back. Sorry about that, everyone. And we go to number 2. And let's go ahead and blow this up a little bit. All right, so we don't always have decay reactions. We have bombardment reactions, we have fission reactions, which is a form of bombardment, and we have fusion reactions as well. But the rules are the same, but you do have to be careful. Just like I say in the text there, you're likely to get particles like neutrons or protons or other nuclides or whatever. And so you still have to make sure that they add up just the same. And so we look over here and says, what is the missing product of this example of fission? Now, fission is where you take a heavy nucleus, which uranium is, uranium-235, and you break it apart into smaller atoms. In other words, fission means you break apart. And so one of the products is barium-138, and we get 3 neutrons out of this reaction. And just like any other balanced chemical reaction, the 3 in front here means that we get 3 neutrons. We get 3 neutrons. So we got to be careful there. But it still works out the same way, where you have to make sure the top numbers are balanced on both sides of the reaction and the bottom numbers are balanced on both sides of the reaction. And so if we do the top on the left-hand side, let me change colors here. And here we go. And that is 236 on the left-hand side. And then we look over here and we have 141. Now it's not 139. It's an easy mistake to say it's 139. But remember, we have 3 neutrons times 1. That gives me 3 on the top. So plus the 138 actually gives me 141 on the right-hand side. Now the left-hand side, since we're dealing with neutrons, is super easy. 92 plus 0, well, that's 92. And 56 plus 0, that's 56. All right, so now we're back to exactly the same sort of situation we had on the previous slide, which is what plus 141 gives me 236, and that would be 95. And so we say 95 over here. And then we say what plus 56 gives me 92, and that would be 36. And so now we look for element number 36, and that turns out to be krypton, Kr. And we can check and go back, 95 plus 141, what is that? That's 236. And sure enough, it's 236 on the left-hand side. So this is good. Now, this is the basis of fission in the sense that it is a neutron, which is the secret sauce that makes fission happen. And to have a sustained chain reaction, you have to produce more neutrons than you put in. And sure enough, this reaction produces on average about 3 neutrons for every 1 neutron you put in. So let's take a look at this one right here. This is a bombardment reaction, which means we are bombarding, which means we're hitting a nuclide with some sort of particle. It doesn't have to be a 4,2 alpha, which is what we have here. It could be another element, and we're combining them. So let's decide what is missing in this reaction. Now, keep in mind what we set up here. The rules are the same, but you have to be careful. You might get neutrons or protons. So let's take a look here. And so I look at the top, we'll change colors again. And what do we get here? Let's see, let's go light blue. And what do we have here? We have 84, 82 on the right-hand side, so I don't really need to add up that. And what do we have here? 37 on the right-hand side. So what plus 82 gives me 84? And that would be 2. And what plus 37 gives me 37? Well, that has to be a 0. And this is your clue. What has a charge of 0? What sort of particle has a 0 on the bottom? And that is a neutron. Now, what's a neutron? A neutron is 1, 0. You can't have a 2, 0, so therefore it must be 2 neutrons. Do you see how tricky this was? It's 2 neutrons. There's no 2, 0 particle. I'm sure we could find one, but not ordinary particles. And so the product of this bombardment here is rubidium 82 and 2 neutrons. So we can decide, well, how many neutrons do we have? Finally, we get down here and we see that we have a fusion reaction. Now, fusion is where we combine light elements to produce large amounts of energy, and it's the process that powers the sun. Fission, we take heavy elements and break them into smaller elements, and that's the process that powers nuclear reactors and nuclear weapons. And so now we need to know, well, what do we have here? And what do we have? So I don't know. But I do know the tops and the bottoms have to add up, and so we say 8 over here, 4 over here. We get a neutron as a bonus from fusion. And what do we have here? So we say 8, what plus 8, what plus 7, pardon me, what plus 7 gives me 8, and that would be 7. 7 plus 1 gives me 8. And what plus 0 gives me 4, and that would be, well, that's 4. And we look and we see on our periodic table that is indeed beryllium 7. So if we fuse a lithium and a deuterium meaning it has an atomic mass number of 2 for hydrogen, we end up with a beryllium 7. So the key to doing these reactions is to make sure that whatever you do, that the top numbers add up to the same on the reactant side and the product side, and the bottom numbers add up to the same. In other words, the atomic numbers add up to the same on the left side and the right side. Keeping in mind, I use the word atomic number loosely because, after all, neutrons don't have an atomic number. And there we go. So let me go ahead and turn this off and stop.